So this video is going to give a brief overview of section 2.4, limits and continuity. And in this section, we go over the definition of what it means for a function to be continuous, as well as 3 scenarios where a function is discontinuous. Let's go ahead and go through that first idea. So the book tells us this definition of a continuous function. It says that if the limit as x approaches c of some function f of x is equal to f of c, then that function is continuous. And when you first look at this totally doesn't make any sense and it's super confusing. And whenever things are written in mathematical terms, it's always 1000% more confusing than it needs to be. So let's go ahead and draw this out and hopefully it'll make more sense that way. So let's say that we have this function, f of x, and our definition tells us that if the limit as x approaches c of some function f of x, let's draw that out, is equal to f of c, then that function is continuous. All right, so the first part, let's look at our limit as x approaches c. So here's our value c. The limit exists at x approaches c, and from both sides, the function is approaching this value 2. So the limit as x approaches c of this function we have here is equal to 2. Okay, and if this limit is equal to whatever the function is defined at that same x value, then this function is continuous. So we go to the second part. Well, what is the value at x equals c of this function? We go in and we say, well, if we were to plug in c, we get this value here, which also is 2. f of c is equal to 2. And so since these two things are the same, since the limit is the same value of what the function is actually defined at x equals c, then that means that this function is continuous. Now, compare that to if I had a function, same function, drawn like this, except there's an open circle there. I'm gonna, define all my points again. So here's c, here's 2, here's 8. Let's go through the same process again. So first we looked at the limit as x approaches c, and we see, all right, so the limit as a function approaches from both the right and the left side is equal to 2 again. Of this function is equal to 2. And then I go to the second part and say, well, what is a function actually defined at that value, x equals c? And if I were to look at my function, I see, well, at x equals c, the function is actually defined at this value up here. f of c is equal to 8. And since this limit is not the same as what the function is actually defined at x equals c, then this function is not continuous. And of course, when it's drawn like this, it's a lot easier to see, well, yeah, this one's continuous, this one isn't. But this is just visually representing what this definition says right here. All right, and so moving on to the second part of the section, the 3 types of discontinuities. Let's go through them. The first one we're going to go through is called the jump discontinuity. And what that looks like on a graph is you have some function that's going like this, then all of a sudden at this value it jumps up somewhere else, and then continues on. The function is discontinuous at that value, x equals c. And if we're going to go through our limit definition again, we see, all right, well, what is the limit as x approaches c of f of x? I go to this function. The limit actually doesn't exist at x equals c because the left-hand limit doesn't equal the right-hand limit. So that automatically makes this definition void since the limit doesn't exist at x equals c. You could, however, go through one-sided continuities and say, well, if I'm going from the left, it's an open circle. So the limit as x approaches c from the left-hand side is still not equal to what the function is defined at. Let me write that down. The limit as x approaches c from the left-hand side of this function is not equal to f of c, since this is an open circle here. But if I were to go from the right-hand side, I'll write that here. The limit as x approaches c from the right-hand side of this same function, since it ends in a closed circle, the function is defined at that same value. So that means from the right-hand side, it is continuous, whereas from the left-hand side, since there's an open circle here, it's not continuous. Okay, our second type of discontinuity for these functions is called a removable discontinuity. And what that looks like on a graph is, if I have something like this, then all of a sudden, there's just a hole in the middle. And there could be a point somewhere else, or it could just be a hole without a value defined elsewhere at that x value. And this is the same example that we went through over here. But going through it again, first we look at the limit as x approaches c. Well, here's the limit. The limit does exist here. So our first point is good. It holds true. But then we compare that to what the functions actually defined as at that x value. And we see that's where the definition falls through. The value of f of c is not equal to the limit as x approaches c of that function. And comparing jump and removable discontinuities, it's always good to remember that removable discontinuities, the limit always exists here, whereas jump discontinuities, the limit does not exist here because it's jumping from one value up to another. All right, and going through our third type of discontinuity, that's an infinite discontinuity. And much as you might imagine, that's whenever the function is going either up to positive infinity or down to negative infinity at some x value. So those are your three types of discontinuities. There's your definition of a continuous function. I hope that was helpful and a good review for this section.